All right, guys, so let's go ahead and talk about 5.1 reaction rates. So first off, how can we determine how quickly or slowly a reaction occurs? This is kinetics. This is what this entire unit's going to be about. And basically, kinetics is going to be the study of the rates of chemical reactions, since there's going to be a lot of factors that influence it. And so we see two examples of some chemical reactions here. We have a fast one that's happening on the left, and then we have an example of a car rusting, which happens over a really long period of time. The rates of these reactions are a lot different, and so we need to figure out what the rates are and how are they affected by different changes. And so when we're talking about reaction rates, we're talking about the change of the reactant or product concentrations over time. You need to know what this equation is. So you need to know that the rate is the change in concentration over the change in time. And we can write that by using a delta for the word change. And so delta just means change, or the triangle just means change. Your brackets are concentration, and so over change, and you can put time as t. This is how you're going to write it. This is what you need to know. And so what is the rate of reaction influenced by? You have 5 different things there's a few more, but these are going to be your 5 main ones. We're really only going to focus on the 4. The physical state of the reactants, if they're in the same state, like 2 gases are going to be able to mix a little bit better. Two liquids are going to be able to mix a little bit better, but that's not going to be what we're going to focus on in this unit. What we are going to focus on is the reactant concentrations, the temperature, the surface area, and catalysts are so important that they have their own section at the very end of this unit. So how do these factors influence the rate of reaction? Well, it comes down to collision theory. The rate of the reaction is going to be influenced by anything that affects the number or the force of the collisions. So if we talk about reactant concentrations, if we increase the amount of reactants we have available, they're going to collide more frequently. If they collide more frequently, the rate of the reaction increases. If we increase the temperature, okay, so we're looking at this picture over here. If we increase the temperature, we're going to speed up the average kinetic energy of each of the individual molecules. If we speed up the molecules, they're going to collide more frequently, and they're going to have more energy when they collide. So the force of the collision is going to be stronger. This will increase the rate of reaction. If we look down here for surface area, this is only going to apply to solids. But if we split this big chunk of solid up, then there's going to be more surface area or more area for each of these molecules that are moving around to hit. If we have more area to hit, again, we're going to have more collisions. The number of collisions is going to be affected, and it's going to increase the rate of reaction. So this increasing the surface area, increasing the temperature, increasing the concentration, all affect the number and force of collisions. Therefore, they're going to affect the reaction rates. We'll talk a lot more about collision theory. It also has its own section a little bit later in the unit. So now let's go ahead and talk about how to calculate the rate in a reaction. So again, we're talking about the change in concentration over the change in time, and we have our molar over seconds as our units. So in this example, we have reactant A turning into product B. So we're going to have A disappearing and B appearing because our reactants are turning into our products. So at time 0, we have the concentration of A set at 1, and we have the concentration of B set at 0. This makes sense because we're starting with reactants and they're going to change into products over time. So now let's go ahead and change this to, let's say that we let the reaction go for 2 seconds. So at time 2 seconds, the new concentration of A is going to be 0.98 molar, and at time equals 2 seconds, the new concentration of B is going to be what disappeared from A. So if we go what disappeared, we started out with 1 and we now have 0.98. That means that we now have 0.02 molar concentration of B. Okay, so all of the reactant that disappeared had to change into product because remember, law of conservation of matter states that we can't create or destroy anything. Okay, it just gets transformed. So we're transforming the reactants into the products at this point. So now how do we go about this? Well, we can talk about the average rate of appearance of B. So let's go ahead and figure out what the average rate is. So the average rate of the appearance of B is going to be the change in concentration over the change in time. So we're going to start off with our final concentration, 0.02, and we are subtracting our initial concentration to find the change. Okay, final minus initial, just like you would do in math. Okay, final minus initial divided by the change in time. Again, final time minus initial time, so 2 seconds minus 0 seconds. That leaves us with 0.02 divided by 2. Okay, and again, use your calculator if you need to, or do it in your head, but we got 0.01 m over s. And that's going to be our average appearance of B, so how quickly B is appearing. So now we can also talk about the average disappearance of A. Okay, they go hand in hand because as A is disappearing, B is appearing. And so we would do the same thing for that one. We would go R equals, and again, we have our final concentration, which is 0.98 minus 1.00, and we are dividing that by the change in time, which is the final time is 2 minus the initial time is 0, and we are left with negative 0.02 over 2. Now, at this point, I have one negative. So I know that this is going to be a negative. So what I have to do is we can't have a negative rate. Rates are always going to be positive. So if you're dealing with the reactant, basically what you're going to do is you're just going to add a negative in the front so that we can have a positive number, and that's going to leave us with 0.01 m over s. And that's going to be our average rate of disappearance of A. Now, we're not quite finished yet because sometimes they're going to ask you to write a general rate equation. And so our general rate equation is basically just using our equation up here. So we have the rate is going to equal the negative change in A over change in time. Remember, I had to add that negative right here, okay, because rates have to be positive. So that's why I'm going to add that negative right there because it's disappearing. And that's going to be equal to the, whoops, I forgot my concentration brackets here. Okay, that's going to be equal to the change in concentration of B over the change in time. Notice how there's no negative here because I didn't need to add the negative because it is already positive because we are appearing. So B is appearing, it's a product. You don't have to add negatives to products, just to reactants. And that's going to be your general rate equation for something that looks like this. So now let's take a look at what that looks like graphically. And I added a little bit extra here because now I have a coefficient. So now I have A is turning into the products B plus 2C. So we have that 2 coefficient in front of C. So to write the general rate equation, okay, it's going to be the same thing. The rate of disappearance of A is going to be negative delta, the concentration of A, over delta time. Okay, we just did that. Okay, that should look familiar. Now, what's that going to look like on the graph? Well, let's say that it looks like this. And that makes sense because we know that the concentration should be decreasing over time, which is what the graph is showing. So now, let's talk about the rate of appearance of B. Well, B is going to appear at the same rate as A because A is disappearing because the molar ratio is 1:1. So the rate of disappearance of B is going to be delta, the change in concentration of B over the change in time. And so when we look at that graphically, okay, it makes sense that we have the concentration increasing over time, and they look pretty similar except they're just kind of flipped upside down. Okay, so they're changing at the same rate. Now, if we look at C, C is going to be a little bit different. Okay, the rate of disappearance of C is going to be the change in concentration of C over the change in time. However, we have that 2 coefficient. So now that 2 coefficient just means that twice as much C is appearing as B in the same amount of time, or twice as much C is appearing at the same time that A is disappearing. So we have to reflect that in our graph. And in order to reflect that, basically you're stretching the graph by a factor of 2, just like you would in math. So you should see the concentration of C increasing more rapidly in the same amount of time. And this is reflected in the graph, as you can see on the right. So the rate of disappearance of A is going to be equal to the rate of appearance of B and half the rate of appearance of C. Now again, remember, the unit for these reactions is molarity over time. Now, let's go ahead and see if we can write a general rate equation using this. So I'm going to write it down here at the bottom. And so I have the rate equals the change in concentration of A over the change in time. But remember, it's a reactant, so I'm going to have to add that negative in the front. And that's going to equal the change in concentration of B over the change in time. Okay, 1-to-1 ratio for these because the molar ratio is 1-to-1, and that's going to equal the change in concentration of C over the change in time. But we have to reflect that C is happening at twice the rate the other two are. So if it's happening at twice the rate, to get them to equal each other, we're just going to have to divide it by 2. Because we have to decrease this amount because of this molar ratio. So you're going to take the coefficient, okay, and it's going to go right down on the bottom of the fraction when you're putting it in front. So this would be the general rate law for this equation. Okay, we're going to look at another practice problem like this. So if you don't quite understand it yet, okay, just hold on. I'll show you guys a different example of it. So if you're already given a rate and you're trying to figure out what the rate of the other molecules in the reaction are, okay, it's actually pretty easy, and all you have to do is use the coefficients. So when the chemical reaction above is carried out under certain conditions, the rate of disappearance of D is 2.5 times 10 to the negative second. What's the rate of disappearance of E and the rate of appearance of F under the same conditions? So according to the equation, okay, we have reactant E is consumed at 3 times the rate of reactant D. I'm just using the coefficients in front. So if it's consumed at 3 times the rate, all we have to do is multiply the original rate by 3. So we're going to go 2.5 times 10 to the negative second, reactants D, times 3, and you should get 7.5 times 10 to the negative 2. Now again, plug it into your calculator. It should be pretty easy. So now that would be the disappearance of E, because again, it's disappearing at 3 times the rate because there's 3 times as much according to the molar ratio. And you can do the same thing for the appearance of F. Product F is produced at 2 times the rate of consumption of reactant D. So that means that reactant D is disappearing at half the rate that F is appearing. So all we have to do is multiply that by 2, and we get 5.0 times 10 to the negative second. So you just use the molar ratio if you're given a rate of one of the components of the equation. So now, let's go ahead and instead of using letters, let's plug it into an actual equation. But it works the same way. And so if we start out with 2 N2O5 and it's creating 4 NO2 plus O2, and we start out with a rate of O2 appearing at 9.0 times 10 to the negative 6 m over s, how would we figure that out? Well, if we want to look at NO2 first, so let's go NO2, and we want to look at the rate, okay, basically we're going to go 9.0 times 10 to the negative 6, and we know that it's appearing at 4 times the rate that oxygen is appearing because of the molar ratio. So all we have to do is multiply this number by 4. Once we multiply that number by 4, we should get 3.6 times 10 to the negative 5 m over s, because it's happening at 4 times the rate. And again, we know this because of the coefficient in front. You do the same thing for the disappearance of N2O5. So we have N2O5, okay? We start out with our original 9.0 times 10 to the negative 6, and we're going to just multiply that by 2 because it's disappearing at 2 times the rate that O2 is appearing because we have that 2 in the front. And so when we multiply this out, you should get 1.8 times 10 to the negative 5. Now, because this is disappearing though, again, I'm going to put that negative in front. And so we have this negative, showing that it's disappearing at 2 times the rate. So now if we were writing a general rate equation for this, okay, we would start out with what the question gave us, so the concentration of O2 over the change in time, and that's going to equal the change in concentration of NO2 over the change in time. However, NO2 is happening at is appearing at 4 times the rate. So in order for these to equal each other, I have to divide this by 4 because it's occurring at 4 times the rate. So I'm going to put that 1/4 right in front. Now again, I got that 4 from the coefficient, so all you have to do is create a fraction right there. And that's going to be the same thing as negative, because now again, we're at the reactants, the change in concentration of N2O5 over the change in time. Now, what do I have to multiply N2O5 by to make sure that it equals these two? Well, it's actually going to be twice the rate, so I have to divide it by 2 to make sure that they equal each other. So now I have all of these are equal to each other, and so that's going to be the average rate of reaction for this equation. And again, the fractions are just coming from your coefficients in the balanced equation. All right, so let's go ahead and look at some multiple choice examples on how this might show up in questions. So this first one, for the reaction represented above, the initial rate of decrease in the concentration of X was 2.8 times 10 to the negative third. What's the initial rate of decrease in Y? Well, if we look at our equation, you should see that we have X as having no coefficient, Y having 2. So that means that Y is going to decrease at 2 times the rate that X is decreasing. So all you have to do is take this number, okay, multiply it by 2, and once you do that, you should get D 5.6 times 10 to the negative third. Okay, in this one, in order to determine the order of the reaction represented above, the initial rate of the formation of XY2 is measured using different initial values of the concentration of X and the concentration of Y. The results of the experiment are shown in the table below. In trial 2, which of the reactants would be consumed more rapidly and why? Well, they're actually giving you a lot more information than you need. This question is asking you what's going to happen to the concentrations of X and Y. Okay, how did they relate? Well, all you have to do is look at the coefficients of X and Y. So the coefficient of X is 1, the coefficient of Y is 2. So you should know that Y is going to decrease faster. And if you look at trial 2, Y even has less of a concentration. But the concentrations at this point don't matter because we already know Y is going to disappear faster at 2 times the rate. And so we can cross out our answer choices A and B, because that's going to say that X is decreasing faster, and we know that not to be the case because of that too. So Y, because the reaction is second order with respect to Y, okay, that doesn't really matter at this point. It's just talking about the initial reaction rates, and so we're not talking about any kind of, we're not talking about the order of the reactions yet. And so it's going to be Y because the rate of disappearance will be double that of X. And that's basically just because of this coefficient to right up at the top. Okay, next, the kinetics experiment is set up to collect the gas that is generated when a sample of chalk consisting primarily of solid CaCO3 is added to a solution of ethanoic acid. The rate of reaction between CaCO3 and CH3COOH is determined by measuring the volume of gas generated at 25 degrees Celsius, 1 atm as a function of time. Which of the following experimental conditions is most likely to increase the rate of gas production? So we're talking about increased reaction rate. So which one of these is going to increase the reaction rate? Well, if we look at A, it's talking about decreasing the volume of ethanoic acid used in the experiment. So The volume isn't going to really matter. The concentration is what's going to matter more. As long as we have enough ethanoic acid, it doesn't talk anything about limiting reactants. So we're assuming that both of these are in enough that there can be a reaction that goes to completion. So the volume is not going to be an impact at all. So decreasing the volume is not going to have an impact. So decreasing the concentration. So if we decrease the concentration, that is going to have an impact, but it's actually going to slow the reaction down because there's going to be less collisions because there's less concentration, so less things to kind of run into each other. So that's not going to be it because it's going to be the opposite. So we want to increase the rate. Okay, decreasing the temperature. Again, this is going to decrease the rate of reaction because we're going to slow those particles down and they're going to collide with less force. So that's going to decrease the reaction. Let's make sure that D makes sense. Decreasing the particle size of CaCO3 by grinding it into a fine powder. Well, this is going to increase surface area, and we know that an increased surface area is actually going to lead to an increased reaction rate, and so the correct answer should be D. All right, and last question. 2 samples of Mg of equal mass were placed in equal amounts of HCl contained in 2 separate reaction vessels. Particle representations of mixing of Mg and HCl in the 2 reaction vessels are shown in figures 1 and 2 above. Water molecules are not included in the particle representations. Which of the reactions will initially proceed faster? So now we're looking at a diagram and we're trying to figure out which is going to proceed faster. We're not dealing with any kind of change in concentration. It looks like all we're doing is breaking up the initial solid. So we're increasing the surface area. So we need to look at an answer choice that has something about surface area in it. If we read A, it doesn't have anything about concentration. All we're doing is kind of breaking it up. So answer choice A is going to be incorrect because, again, nothing to do with concentration. The reaction in figure 1, because the Mg in figure 1 has a larger mass, well, again, if you break a solid up, you shouldn't be changing the mass at all. So we're not changing the mass. Answer choice B is wrong. The reaction in figure 2, because more Mg atoms are exposed to HCl in figure 2 than in figure 1. That sounds like it could be right. Okay. The reaction in figure 2, because the Mg in figure 2 has less surface area than the Mg in figure 1. Well, actually, if we crush something up, we know that we have an increased surface area. So that means that D is wrong and C is our right answer because of the increase in surface area.